Welcome back. In today's lecture, we are going to talk about equilibrium and stability. In the early stage of this lecture, we looked at the concept of the entropy maximum for defining an equilibrium condition. Okay, so the earlier definition of what we have used was something called entropy maximum principle. So, I am going to just write it down. This is something which we have used to obtain conditions such as temperature equality, pressure equality and chemical potential equality for an equilibrium system. So, the definition is that the equilibrium value of any unconstrained internal parameter is such as to maximize the entropy for the given value of the total internal energy. So, for given internal energy, the system tends to maximize the entropy, okay, in order to achieve the equilibrium condition. So, that is what we used in the earlier stage of the course, and we used the maximization of entropy to obtain various different conditions. Now, what we are saying is this particular concept or principle is equivalent to the energy minimum principle. Okay, which says that the equilibrium value of any unconstrained internal parameters. So, it says the equilibrium value of any unconstrained internal parameters is such as to minimize the energy for the given value of the total entropy. So, it says that for a fixed entropy, the energy is going to get minimized to achieve the equilibrium state. Okay, that is what it is saying that. So, these two statements or two principles are equivalent. So, in other words, what we are saying is the following, that for the case of the first, u s is a function of u v n. So, for a given u, we are saying that the first derivative with respect to some dummy variable x at a constant u should be 0, and the second derivative x should be less than 0. So, this is because this s has to be maximum. So, this is the definition of the maximum. The first and second derivatives should be 0 and less than 0 respectively. Now, this we are saying that this is equivalent of saying that if we consider u as a function of s b. So, for a given total s, okay. So, this is equivalent in some sense. Okay. So, let us try to get this proof of kind of equivalence. So, in order to get that, let me just first consider the following. So, the question is how do you prove this? So, let us consider the chain rule, okay, where x could be anything here, this must be 1, okay. right. So, you have S u x, and that is what this relation we know. Now, this implies that we want to understand, we want to obtain this relation again. So, this is nothing but del u by del x at constant s, that must be minus 1 by del s by del u x del x by del s u, or del u by del s x and del s by del x u. Okay. Now, by definition, the derivative of u with respect to s is nothing but t. So, this is nothing but t del s by del x u. Okay. Now, for maximum entropy, or in general for equilibrium, if you consider this, then del s by del x at constant u should be equal to 0. So, this at maximum x should be equal to 0, which essentially means del u by del x at x should be also equal to 0. Okay. So, this we are trying to get the equivalence of these two different relations, which we are saying that these are both equivalent. So, for a given s, u should be minimum, or vice versa. Okay. And we are talking about unconstrained at this point, internal variables. So, let me also get the second derivative. Second derivative we have to prove for minimum u, this should be negative. How do we do that? So, let us first start with the expression. Okay. We want this to be evaluated. So, let me just break this again here, del u by del x. Okay. For the sake of simplicity, we are saying this as a m. Okay. This as m, then it becomes del m by del x, okay, at constant x. Okay. So, we need to find out this. Now, m is basically a function of u and x. Okay. From the definition, you can clearly see m is a function of u and x. Hence, I can write dm as d del m by del u constant x du plus del x constant u del x. Okay. So, this is by simple, if you do take the differentiation. Now, since we want del m by del x, so I take this, I differentiate this with respect to x. So, del m by del x, keeping s constant. So, this will be del m by del u x, del u by del x, keeping s constant, plus okay. Now, this will be 1, and what about this at extremum? So, at extremum, this should be 0, as we have already defined it here. So, which essentially means that the second derivative del m by del x s is nothing but del m by del x u. So, this is what we can obtain from this derivation for the case of extremum. Okay. So, now we go back and put the variables here. So, this is nothing but del square u by del x square s, that is by definition, that is del m by del x was nothing but this, right. And now I can write it this as follows: del by del x, del u by del x s. So, if you look at this expression on the left hand side, I can simply write del square u del x square s, that is by definition of m. And now, on the right hand side, which we have derived it, that this expression is equivalent to this expression, I plug in the definition of m here, which is nothing but del u by del x s, but then u is constant here. Now, here at this point, what we can do, okay, this is the point we can represent this del u by del x s, which was used earlier, as nothing but minus t del s by del x u. Okay. So, this is nothing but minus t is a constant here, and I bring here T del S by del X U, okay. This is what we defined earlier. This was U at a constant U. So, this comes here as U. Now, with this we have now the expression minus T del square as del X square U, okay. Now, this we know at extremum, if you look at the definition, this must be less than 0, okay. So, if this is less than 0, that means this is less than 0, that means this is greater than 0. So, essentially this gives you the second condition, del square U del X square S is greater than 0, and of course, the first derivative del U by del X at constant S is equal to 0. So, this is something which we had derived, and that means if you look at the original question was that this principle was used to evaluate the equilibrium conditions by maximizing the entropy for a given internal energy. Okay, this is equivalent to saying that U is minimum for a given entropy. Okay. So, that is an important aspect. Okay. So, this essentially can be drawn also. So, one can come up with this kind of diagrammatic explanation of this, that for S as a function of x, which is the unconstrained variable, okay, this reaches a maximum for a fixed u v n, and this is equivalent to saying that u or some kind of this u as a function of again x unconstrained variable, and this is something which we get x equilibrium. So, this is x, okay, for a fixed S v m. Okay. So, this is something which is equivalent, that is something which we have just derived. So, using this concept of minimum energy, we can actually try to again evaluate the conditions of equilibrium such as thermal equilibrium and so forth. So, for the sake of illustration, I am going to just do one example. Okay. So, this would be just establishment of thermal equilibrium, and similarly you can do that for pressure and chemical potential. So, establishment of thermal equilibrium using energy minimum principle. Okay. So, consider the closed composite system, okay, so with a rigid, so we can draw it like this, let us say. Okay. So, this is rigid, impermeable, and dithermal. So, essentially the heat can exchange back and forth, okay, but it is a closed system. Okay. And is a composite. So, it is a closed composite system. So, what is the total energy of this overall system? We can write it U as U S1 V and N and so forth, right. So, the 1 stand for this could be 2, first compartment, second compartment, okay, and this plus U of the second one, okay, whereas here would be sec of the second, and similarly for the V and N. So, what we know is that total volume and number of moles, these are constant and known. So, total energy is fixed, okay, and in the initial stage S1 and S2 can change because of the heat exchange. Okay. So, we can write du as du1 plus du2, and since there we are saying that the only contribution is through the heat. So, the change in the internal energy for 1 and 2 are corresponding to the heat, and we can write it there considering is an equilibrium process, a slow process. We can write this directly as this. Okay. So, this is something which we can write. Now, this has to be 0 because total energy is constant. Okay. Now, we also can consider that at equilibrium, of course, at equilibrium what is the conditions of this temperature. So, at equilibrium of course, we are considering that the total energy will be fixed here, and thus we can write that S1 plus S2 should be constant, du as T1 minus T2 ds1. Okay. And this equality indicates your T1 should be equal to T2. So, just considering that the energy is minimum, or considering simply du, we can obtain this thing. If you recall that earlier exercises, we have just made use of ds equal to 0 as far as the total ds is concerned here. So, we are not making use of that at this point, but of course, if you can clearly see here, we made use of the total entropy is constant. Okay, that from the different perspective here. Okay, so you can do these similar exercises for the pressure equality and chemical potential equality. Okay. So, what we are going to do is we are going to change these conditions. Now, we will be using the energy minimum principle to find out what is the thermodynamic variable which we should look at if we change the natural variables. So, as of now the natural variables are SVN for the internal energy, but since we have now developed thermodynamic functions for different different conditions of the natural variables. For the case of a TVN, it is Helmholtz free energy. For the case of a TPN, is Gibbs free energy. So, considering those changes, what is the natural variables or changes in the natural variables or the corresponding thermodynamic functions, or considering different constraints, what would be the conditions on the thermodynamic functions if there is a change in the equilibrium state. Total let us say composite system at UVN, we still can consider that, but our systems or the system which we are interested in is at TVN. By making sure that you have a dithermal rigid wall, but heat is being exchanged with a bath which is at temperature T. Okay. So, this could be a TB. Okay. So, with this bath essentially the system temperature will reach at T, and so we can consider this to be all isolated. So, total composite could be total energy U V N N. Okay. Now, with this we can apply minimum energy principle, okay, and find out what is the appropriate variables which would give the indication of equilibrium condition, or another word, what would be the conditions of the thermodynamic functions associated with TVN. Okay, will it be positive, will it be negative? So, that is something which we would like to lead to that kind of conclusion. So, let me start with this basic definition. So, essentially U plus UB should be minimum, that is what it says, that right, at equilibrium, okay, subject to total entropy is constant, S plus SV is equal to constant. Okay. So, that is what we are saying. So, because minimum energy principle says that the energy will be minimum for a given total entropy. So, for a given total entropy, the U plus UB has to be constant. So, this would give us two conditions. One is d of U plus UB should be equal to 0, and the second derivative d square U plus UB should be greater than 0. Okay. So, again subject to the d of S plus SB is 0. Okay. And the other thing which we know that this is a rigid here. Okay. The only thing is dithermal. Okay. So, rigid and dithermal, which essentially means that your dN and dV, these are going to be 0. Okay. What is this expression? So, this is du plus dub should be 0, and du this is nothing but dq plus dw, right, but there is no work associated with this bath because of the rigid walls. So, this is nothing but your Tb dsb. Okay. Now, from here we know that ds is nothing but minus dsb. So, therefore, du minus T ds. Okay. Right. So, the other thing which we can do is that we can also write the du in for the system, and this would be nothing but again T ds minus Tb ds. So, this is the expression we have now. Now, I can write ds in terms of Sb also. So, from here I can obtain T minus Tb. Now, with this you have T minus Tb ds is equal to 0. So, this would mean that T is equal to Tb, that is the condition of thermal equilibrium, essentially very intuitive, but from this exercise we could get that. Okay. But our intention is to find the appropriate thermodynamic function which would be indicative of the equilibrium condition for such a condition where you have fixed the volume, temperature and number of moles. Okay. So, in that case let us consider this expression again. So, that is fine as far as the thermal equilibrium condition is concerned. So, now consider again. Okay. So, this is the condition of, this is the minimum energy principle here. Here I am going to represent this u as this as simply du minus dB dTs, that is something which we have written here, right. Now, this dB is a constant anyway, because the bath temperature does not change. Bath is supposed to have a large volume where this heat exchange would not change the temperature of the system. In that case I can write this as du minus, right, but Tb is nothing but T here. So, this is, we can write u minus Ts is equal to 0, and u minus Ts is nothing but Helmholtz free energy. Okay. So, that means one of the condition is of course that dA should be equal to 0 for such a system here. Okay. Where we are maintaining the temperature, volume and number of moles. Now, let us look at the second derivative, that is the d square u plus ub. Okay. Again we can write this as d of du plus dub, and this can be written as simply again back from here I can get it u minus Ts greater than 0. Okay. So, right, and this is nothing but d square a greater than 0. So, this indicates that both this condition indicates that for the case of such a system where you are maintaining temperature, volume and n, your u minus Ts must be minimum. So, u minus Ts or A is minimum at equilibrium. So, something which we have derived. Okay. Other thing which we have derived from this is of course the temperature equality. Okay. So, that was for this constraint where we put temperature. Of course, you can extend this understanding and analysis for more difficult conditions. Now, what we have done is all this derivation was at an equilibrium. So, but you can also consider the case where you are a little bit off equilibrium. In that case, your entropy is not going to be constant, is going to be greater than 0, total entropy. So, how do you do that? What will be the appropriate variables which you are going to get as far as this Helmholtz free energy is concerned? So, let us look at it. Okay. Because in your case you can clearly see that dA is equal to 0, the first derivative, and second derivative is greater than 0, that means A is to be minimum for such a condition. So, now let us little bit extend it so that we can understand the complete picture here. So, consider for any process that takes place from an off equilibrium to an equilibrium state. Okay. So, we are considering a process which takes from an off equilibrium and going towards an equilibrium space. In such case, your total entropy should be greater than 0. Total energy still remains 0. So, this is du plus dub is equal to du plus dB TSB, right. This is still equal to 0. Okay. So, we are still considering slow and reversible process. So, in this case I can write this as, right. So, this is nothing but your ds plus dsb, okay. This is greater than 0, okay. Remember that. So, by definition we can now write this as du plus, so here SB can be written as because this is dst can be written as t dst minus t ds, this is equal to 0. So, because we are considering temperature to be constant here. Okay. So, or I can rearrange this thing that TDS T is TDS minus du. So, this we have considered to be simply T here. So, with this I can now plug in here, I can consider this as minus T of d dTs, this is du minus TDS, and since T is constant here considered to be equal, already the temperature equality is there, then u minus Ts. Okay. So, this anyway is going to be because dTs is greater than 0, this has to be negative 0, then this means this has to be less than 0, which essentially means d of A equal to less than 0. So, what we this by doing this simple exercise is, when you have a process that takes place from an off equilibrium to an equilibrium state, the Helmholtz free energy tends to reduce, and eventually at equilibrium the dA is going to be 0. So, it will reduce until the point it equilibrium reaches. So, you can draw this like this. So, you have A and some x is unconstrained variable. So, it is going to be like this. So, if you are like here, then if you are like off process going towards minimum, then essentially the dA has to be less than 0. Okay. Similarly, for the case of whether it is off equilibrium here. So, this is your x equilibrium for a given t Vn. Okay. So, you can do these exercises for other cases as well, but for now I think we can stop and we will take this further in the next class. Okay. So, see you in the next class.